Hello. We originally planned to have 3 presenters today, Michael Wong, myself, and Meg and Michael. Unfortunately, the airlines had other ideas, and so I'll be doing my best to impersonate the impersonable or irreplicable or whatever, Michael Wong. Or imitate the imitable, and whichever. In any case, we're going to be talking about the exciting new performance of Safe Memory Reclamation. Obviously, since we have Meg and myself here, we'll be focusing mainly on hazard pointers and RCU, but we'll mention some other possibilities as well. And this slide is for the usual disclaimer, and I'll let you decide how the transitivity works between them being mine or Michael's then mine or whatever you want there. We have Code Play Legal's team slide here, and Code Play's slide, and now an agenda. So we'll start off on why we want this in the standard in the first place. And the thing is, we need end-to-end atomicity in many cases. We need the information to come in to actually be processed and come out the other side in some organized fashion. That's the way of information processing. And life can be uncertain. Some of you may have learned that more emphatically than others. But I can assure you, even for those who have learned it less emphatically, that life is uncertain. And trading uncertainty, accepting greater uncertainty for performance, is a big part of life and of computing. And that's primarily what we're talking about here. So of course, we've got Schrodinger's cat here. Being simultaneously dead and alive in the box gave me an incredible perspective on the life, the universe, and everything. And I'm here to tell it to the world. The thing is, even if you have a non-Schrodinger's cat, if the cat changes state, perhaps less dramatically than becoming alive and becoming dead, but if the cat changes state, it takes time for that information to propagate from the cat to the computer system. So whatever data you have reflected in the computer is out of date by the time it hits the computer's memory. And we can leverage that fact and have a slightly more out of date and get much better performance. And that's, again, what hazard pointers and RCU are about. And here's a common pattern that happens a lot. Okay, we require a lock. While holding that lock, we've got the state pinned down because people are playing nice and not messing with it unless they're holding the lock. So we compute some property of data protected by that lock. We then release the lock, at which point anybody else, anywhere in the system, could acquire the lock and just totally change the data arbitrarily. Nevertheless, for some period of time after releasing the lock, we use the computed property. This pattern happens a lot, and this instance, I believe Picus mentioned this last year, is one case where using deferred reclamation makes sense. You're using out-of-date information anyway, so why not just go with that and get some increased performance as a result? And these are some approaches to doing that. You could also add garbage collectors if you wanted to. Again, we'll be focusing on RCU and hazard pointers, and I guess transitively on snapshot. There's a gentleman over there that would be a great person to ask about snapshot if you want more detail than I'm going to give you. Jeffrey Romer. Okay, we have a problem with fundamental physics here, and that's that the speed of light is finite. And so thus far, I mean, there was some interesting excitement a few years ago about neutrinos that turned out to be a bad connector or something like that. But as far as we know, there's no way to propagate information from point A to point B any faster than the speed of light. Well, okay, that might be a problem, but we can just make things smaller, right? I mean, if we make a computing device be 0 size, then the speed of light is irrelevant. Unfortunately, there's also something called the atomic nature of matter. We can split atoms. We've been able to do that for, what, 70 years now, 75 years, something like that. The problem is that after you get done splitting them, the atoms aren't really in any kind of shape to be used in electronics, at least not electronics as we know it today. And so we've got these 2 laws of physics that are really constraining us. And there have been transistors like this with a single row of atoms actually produced and used in research environments. And the last time I saw a scanning electron microscope of a transistor was more than 10 years ago, and it had about that many atoms in the base. So it's entirely possible that they're doing this in production. It's entirely possible this laptop is like that, for all I know. But it's close. So we can only go so much smaller. Now, I can't help noticing as I look out in the crowd that the average age of the audience is somewhat younger than myself. So perhaps some of you young, energetic people can solve this problem and get something going faster than the speed of light and smaller than an atom. And I would salute that. That'd be really cool. I'd like to know how you do that. But until you do, I'm asserting that these things are limiting us and we have to live within those limits. And this is one of the reasons we have things like deferred reclamation. Okay, so let's take a look at what we have for deferred reclamation. We'll just take a quick look at a few things. Atomic shared pointer. In this case, we can have reference counts, essentially. It's an organized way to concurrently reference count in a safe way. It guarantees atomic access. It can be implemented more efficiently than that over there. And in fact, thanks to Anthony Williams, we have some pretty nice implementations. I'm not going to say they're optimal, but they're better than we've had in the past. So you can use locks if you want, mutexes if you will. There's a is lock free that checks things out. If you have a double compare and swap, you can do it lock free, and that's wonderful. Thing is, though, if you're using this, your readers are writing to shared memory every time they update the reference count. And the resulting cache misses are really painful for your performance and your scalability. Don't get me wrong, this is a wonderful thing. There's a great place for it to be used. I'm not saying don't use it. But if you want the ultimate in performance for mostly readers, this might not be your best choice. Snapshot is a kind of an interesting novice-friendly, for some definition of novice, way of having information that changes at any time but changes rarely, and having it so you can get a snapshot of information and work on that, and have it so that you don't have to worry about these horrible races between I'm getting a reference to this and somebody else is getting rid of it. It takes care of that for you. It's a standard deferred reclamation based on RCU hazard pointers or reference count. They prefer RCU, which of course I fully support. Other people may have other opinions. But you use this when you're mostly reading, and that's true of most of these sorts of approaches. Now, we strongly discourage, but we don't prohibit. We strongly discourage, but don't prohibit the trivial implementation where when you update, you just throw the old thing on the floor, you just leak it. The reason we strongly discourage it is that having your system run out of memory after a while is kind of a bad form. On the other hand, if you know you're only going to update once a month, and you know that you're going to take the system down and reboot it every year, it's really simple and straightforward, and what's the problem, right? But again, there's trade-offs. Question? Go ahead.
Can I interject one small amendment? It's not designed for novice users. It's designed for users who aren't specifically concurrency experts.
Okay.
For general programmers, essentially.
Very good. Thank you for your definition of novice. For some definition of novice, there's your definition. Thank you. So we aren't talking people that. Well, I've seen some very young people. I mean, you know. Single-digit age that were really impressive with concurrency, but I wouldn't count on all such people having that knowledge. Okay, so there's the latest paper. There might be an update out soon, but I'll ask Jeff what's going to be showing up there. This is a snapshot of the API. I'm not going to dwell on this, but it gives you an idea of what's involved. And then let's go ahead to a new concurrency chapter, as opposed to a new chapter in concurrency. Although maybe we have that too, who knows. So Concurrency TS1 was published in 2016. The stuff didn't make C++17, although some of it maybe gets into C++20. And things have changed. And that's kind of the purpose of a TS, is to put stuff in there, learn how people really use it, and get something that's beaten upon and actually is appropriate for the standard. I suppose the executors guys might complain about having too much learning, but nevertheless, that's the purpose of it, and and we've seen that happen. Now, TS2 will have a number of things in it. I'm not going to go through these in detail, the new executors there, but also at the end, some of the deferred reclamation synchronization primitives. In particular, we're going to add a new section. That's the 33.6 down there in the lower right-hand corner for you guys. And we're going to move the atomic specialization of shared pointer there. We're going to have snapshot, Jeff stuff. We'll have RCU, and we'll have hazard pointers. And so we'll have a TS2, it'll have this in it, and this will be a way for us to see people get implementations and see how things are used and see what we really need for a later IS. Okay, so we've got all these different ways of doing deferred reclamation. Which should you use where? What's going on? Okay, well, there's a bunch of things they have in common. They've got a basic idea that's similar, as you can see. They have a scope that's rather similar, word for word identical, in fact. There's different degrees of composability. Current hardware supports them all, which is a nice thing. We have existing APIs, experience, and all that. So they're all the same so far, so what's the point, I guess? And the point is that they do have somewhat different properties. And I'm not going to go through this in detail. There's some places where RCU and hazard pointers shine very well. Reference counting works very well and has for longer than I've been alive, which is saying something in my case. And the cool thing is that Maggot in his section will be talking about changes. This table is not something that's set in stone. It changes as things come along, and Maggot in his section will be talking about some things that will change this table. So please stay awake and stay here for that. And now I'll take off my Michael Wong hat, and I don't know whether I put on a Paul McKenney hat or if that's what I get when I take off the Michael Wong hat, but either way, I'll go forward to the next presentation here. And let's see if I can make my mouse work here while looking backwards. We'll do that, and then we'll do that, and then we'll do that. Ooh, the technology worked. Don't worry, it won't happen again. So here we're talking about RCU. This is primarily talking about the state of the proposal for TS2, the C++ bindings. So we're talking about what the API looks like. We're going to talk about some use cases, some usage restrictions, and if we have time, some learning opportunities. Okay, so it hasn't changed a whole lot. We have RCU obj base as the intrusive interface, and you use CRTP style inheritance, and it adds this structure to your data structure that's going to be protected. There's a member function called retire. When you know that you've removed the object from readers, you can call that, and then when it's safe, it will delete it. And you can supply a deleter or take the default, as you choose. We'll look at RCU reader on the next slide. It's a pretty standard RAII style of thing. RCU synchronize used to be synchronize RCU, but we've aligned it, so we have RCU underbar in front of everything. And it waits for the old readers. So if you had a reader that was in effect when you called RCU synchronize, that reader will have completed before RCU synchronize returns. RCU barrier is kind of the next stage. It's for retires. What can happen is you might, if you just are using delete, the system delete, you don't care. Because whatever, it gets deleted when it wants to and everybody's happy. But if you're using a custom allocator and you wanted to destruct that allocator, it would be a really good thing if all the deleters for that allocator were done before you destructed the allocator. And that's what RCU barrier is for. You've got all your retires are out there, they've executed, the deleters might not have yet, but then you do an RCU barrier, and that waits until all the deleters are done, and at that point it's safe to destruct your custom allocator. And it can also be used for other shutdown style things. If you don't like intrusive interfaces, we have a non-intrusive version on the bottom. You just, a free function, RCU retire. There, of course, is never a free lunch. And the lunch you get to pay for in this one is that this might call the allocator. A high-quality implementation will almost never call the allocator, but it might. Whereas the top one is guaranteed never to call the allocator. All right, so let's look at the RIA reader. I'm not going to spend a whole lot of time on this. If you've seen LockGuard and things like that, this is very familiar. You just declare it, and it has a constructor. It has you can put a defer lock T, so you can do the usual thing of assigning them back and forth in case you get one down the subroutine stack somewhere, and get rid of them later. All right. This diagram shows how these things relate. I'll go through this really quickly, but the slides will be up at some point, and if you haven't used these sorts of things before, this is a good slide to kind of organize how it works. And the key thing is, if we had a reader up there in the upper left-hand side, and some part of that reader, the constructor, for example, happened to be for a retire, well, that reader might see the state before something was removed from the data structure. And so we need that reader to complete before the deletion happens, because otherwise the reader could end up with a reference to something in the free list. And that's bad form. So this is the guarantee it makes. If your constructor happens before the retire, RCU guarantees that your destructor, your reader's destructor, will strongly happen before the deleter. So if you have a chance of seeing the early old version, you're guaranteed to be done and gone before any destructive thing happens, like a delete. On the other hand, if the deleter happens before your destructor, that means you can see this thing go away, then you're guaranteed that the retire, the corresponding retire, strongly happens before your constructor. In other words, if you might see the deleter, the results of the deletion, you're guaranteed not to see the early state where you might have been able to get a reference to the thing deleted. So that's kind of the two ways that ordering happens for RCU and readers. Okay, so that's the readers. We have barrier as well, and that looks kind of like the bottom half, but the arrows are the other way. If a retire happens before the RCU barrier call, then the deleter is guaranteed to strongly happen before the return. And this is, again, the thing we want if we have a custom allocator that we want to destruct. We want to be able to wait for all the deleters to get done so that everybody's done with it, and then we can destruct it safely. Okay, use cases. This is the one in the paper. We have a name up there at the top, and we want to be able to access this name, maybe print it, maybe put it somewhere, whatever, copy it, whatever we're doing with it. And all we have to do is do an RCU reader there, the RR. That does an RAII, which stays around until the close curly brace. Because Bozo here hasn't got memory order consume that everybody likes and that works, we still use the memory order require, or volatile if in the Linux kernel. And once we've done that, we can use S freely, knowing it's not going to go away until RR goes out of scope, in which case anything might happen. The updater is straightforward. We do an exchange, an atomic exchange, that puts in the new name and returns the old name atomically. So we have the old name, we pass it to retire, and then in the fullness of time it gets deleted when it's safe to do so, once all the readers running right now are done. Okay, so that's kind of the basic use case, a simple use case. We can also, we may need to clean up. So the first part all the way down is the same, aside from comments being removed. And we've got this new function on the bottom, shut down RCU cleanly, and it invokes RCU barrier. So if we have our custom allocator that we've been using for all this stuff, once we get done doing our last update, we're not doing any readers anymore, we can do shut down RCU cleanly. And when it comes back, all the retires will have done their deleters. Nobody's using that allocator anymore, so we can safely destruct it. And this next one is similar, except we're using the synchronous primitive. We're using RCU synchronize. In this case, we don't have any behind-the-scenes action. We do the RCU synchronize. When it comes back, all the readers are done that might have been using that object. We can just delete it, just in line. The cool thing about this one for user space RCU anyway, this different implementation might do different things. If you only use RCU synchronize and never use retire for user space RCU, then you don't have any background threads. Okay? We'll talk about that a little more later. Users restrictions. We've been having some fun with shutdown. The Linux kernel is very straightforward. At some point, things just stop, and then you reboot or something, right? That makes things quite simple. On the other hand, if you're doing this with an application and you have some memory leak detection tool, you might see a whole bunch of stuff that looks like it leaked just because it hasn't got its deleter running yet. And so one way of dealing with that is have a container wait for its context to destruct and defer free. You can make each container's destructor do an RCU barrier. If you have a huge pile of containers and can't run their destructors concurrently, this might be a bad idea. Another approach is to split the destructor so that before you retire, you execute the destructor, leaving just a bare chunk of memory, and you pass the bare chunk of memory to retire, and then the deletion just frees memory. It doesn't have any other action and can be safely deferred. If you do this and the user has some reference, for example, an iterator, then you also have to have the rule that those iterators or whatever are totally done and taken care of and deleted and destructed before the iterator, before you destruct the whole structure. There may be some other options, and that's part of what we hope to find out in TS2 is how else would you do this? What would best work? Again, the other approach you have is just to never use retire and always use RSU synchronize, in which case everything is synchronous and everything is there. Now, one trick with this is that it is perfectly okay for a deleter itself to invoke retire. In fact, it's possible for a deleter to invoke retire, which has a deleter which invokes retire, and so on, forever. Things like this actually happen in the Linux kernel. At which point, you're never going to ever be able to wait for all the deleters to get done, because there's no end to them. One way is to have some kind of a communication where you say, look, we're shutting down, and don't call retire anymore. Another way is at some point, maybe you do a few RSU barriers to let people get out of the way, and then say, all right, we're done, and shut down uncleanly. But that's one of the reasons. This is one of the things we'd like to explore further and see what the TS says. These are a list of things that we hope to learn. I'm going to just go through a couple of them to give Magid time to go through his examples. The first one is RSU domains. And one of the things that comes up if you have any kind of object-oriented thing is, shouldn't this be object-oriented and have domains, separate chunks? And in fact, in the Linux kernel, we have something called sleepable RSU, SRSU, which has domains. The thing is, if you have a domain A and a domain B, the thing that's nice about that is if you have a long-running reader in domain A, that doesn't delay the updaters in domain B. So that's kind of a nice property. Again, there's no free lunch. And the downside of that is that you've split the updaters, and you've also reduced the amortization of the update machinery over the number of updates. In the Linux kernel, this is not a subtle effect. It's not at all hard. You can take a big tarball and expand it and then delete all the files, rm-rf it. And you'll end up with thousands of updates per grace period. And that means the overhead of the grace period computation is amortized almost nothing across those thousands of updates. If you have lots and lots of domains, you've reduced the effectiveness of that amortization, which may be okay, but it's something you should know. It turns out SRSU isn't heavily used. We'll look at that in the next slide. And that's not because it came in late. It showed up in 2006, and normal RSU showed up in 2002. So they've been in the kernel not that much difference in time, both way over 10 years. However, we may need domains. It could be that there's some people that believe that GPGPUs, if you do RSU and GPGPUs, you have to have domains. Maybe they're right. And there's some people that believe that if you're going to do portable libraries and generic code, and you want to work nicely, you need separate domains, and perhaps they're right too, and hopefully experience with TS2 will give us good answers to these. Just to give you an idea, in the Linux kernel, if you take all the instances of calls to the global RSU API, there's almost 8,000 of them. If you look at all the calls to the SRSU API, there's less than 500 of them. So that, of course, keep in mind that the Linux kernel is written in C, not C++, so our mileage might vary. If I was relying strictly on this kernel, on the Linux thing, I'd say, don't even think about it yet, but maybe C++ or maybe GPGPU is needed. Deleter context. Well, as we said earlier, the thing is that you have to run the deleter somewhere. Something has to run it, and we don't specify where. That's up to the implementation. Some use cases get really bent out of shape if there are background threads created, although the background thread is very convenient because you don't have to worry about deadlocks or conflicts. If you are holding a lock across some call to retire, that's okay. You have another thread somewhere that never acquires that lock, runs the deleters. If the deleter also acquires that lock, no harm done. However, if we say we're not going to have background threads, we have to run the deleters from somewhere. That somewhere might be RSU barrier, which would be, it wouldn't add any more restrictions, but RSU barrier is very rare. It's normally called only during shutdown events. So maybe you want to call it from retire. Well, at that point, suddenly, if you're holding a lock across a retire, which is a very common pattern in the Linux kernel, and you're acquiring that lock in the deleter, which is, again, a common pattern in the Linux kernel, you got a deadlock problem. So we may need to worry about that. The other thing is that some environments that say we don't want any background threads, period, if you talk to them a little bit, will say, well, okay, if we have control over where and when the background threads run, that's okay. And so it may be that there's an approach there that works for people. And again, to repeat yet again, if you just always use RC synchronize and never use retire, you don't need a background thread. Okay, the other thing I'm going to skip just based on time, and we went through the clean shutdown fairly well. So we've got a C++ RCU API. We've got the memory ordering well defined. That's something that happened over the last several months. There was quite a bit of controversy over exactly what guarantees need to be there. I think we've got that laid out. We have some sample use cases, and I'm looking forward to learning experience from the Concurrency TS1, although perhaps not too much learning experience, but we'll see how it goes. Anyway, what we're going to do now is we're going to switch laptops. I'm going to disconnect mine. We can take questions if people have them right now, and you know, if not, talk among yourselves or whatever. So questions, comments, thoughts?
Thanks.
I guess I need that too. Yeah.
I'll also add a quick question of what's the timeline for TS2?
That is something I don't know for sure. It's something that the initial deadline for it, I think, is passed, and it's a matter of getting things set up. It's a matter of getting all our things organized. We have to get these proposals through the various committees to say okay for TS2. So we need to talk to Library Evolution and Library and go to the next step. Hopefully this happens in San Diego in early November. Okay, thank you all very much, and I give you Meg and Michael.
Thank you. So I'm going to talk about the hazard pointer part. And very briefly, I'll describe the basic algorithm. So a hazard pointer is a single writer, multi-reader pointer. And the way, when a thread writes the address of an object to a hazard pointer, what it's doing, it's announcing to other threads that if they remove that object after the hazard pointer is set, and then they cannot reclaim that object until, as long as the hazard pointer continues to point to the object. So that's that's the central guarantee. I have an example here of there's like a source pointer pointing to an object, similar to the example we use in the proposal papers for the committee. So from the protector side, which is like the reader, they are basically setting the hazard pointer to the address of the object that they want to protect, and then they check the source that actually the source is still pointing to it. It's like it's not removed. The important thing, it hasn't been removed yet or retired, as Paul alluded to the API. So from the reader side, that's the guarantee. It's like, okay, they were able to set the hazard pointer before it got removed. From the point of view of the remover, they replace A with, they replace A with B. And then if they want to reclaim object A, they actually check, are their hazard pointers protecting it or not. As long as the reader is protecting the object, then they cannot reclaim it. Once the hazard pointer changes, then they are free to reclaim it. Anyway, that's kind of like the basic algorithm. Now we're going to take a look at the API for Concurrency TS2. And I'll spend like some time on that, but most of the time I'm going to look forward beyond that. So for the TS2 API, the main objectives there were we want something useful that actually supports common use cases, and also to have API that actually will help us learn from the TS process to get feedback on implementation and usage. In addition, also, we actually managed to put a complex memory model there, so that was a good exercise to do that as part of this proposal. And otherwise, it's mainly minimalist, because we don't want to put a lot of stuff that actually might not be useful and delay the process. But beyond that, we plan to add more details that actually give the users more control. For reference, the latest paper is P0566. The latest one is R5, and we're not going to do more. We'll add more to that code, but then the next paper for San Diego meeting will be P1121. So we're preparing that for the mailing. So here's the API. The first thing is domain, and I'm not going to spend too much time today on that. Basically, it is for letting threads like not interfere with each other in cases where the usage pattern is actually, so different that actually is good to have separate domains. But if a user doesn't want to use domains at all, they don't need to type the word domain. So there's a default domain that will be used by default. Cleanup is similar to RCU barrier, where say reclaim everything that is reclaimable, that's not protected. So it's kind of not exactly the same as RCU barrier, but similar in that. These are the main classes that actually I'll talk about more about. Is like there's a base class template for objects that are protectable by hazard pointers, and then there is the class for hazard pointer itself. So I'll start with the protectable objects. It's a CRTP inheritance where the derived type is a template argument of the base class template. It allows us to call the functions of the base template and to by default get the default deleter for the type that actually the derived type. Here we have the customizable deleter. If someone wants to use the default deleter, then of course they don't need to specify that. And the main function is really retire. It's saying, okay, now we call retire only when the object is already removed. Like nobody can protect it anymore. And by calling retire, we're passing the responsibility for reclaiming the object to the library, to the hazard pointer library, when it becomes unprotected. We're going to look at the usage example here, where we can see here that the protected type obj is inheriting from obj base. And we see here that we have to remove the object that we want to retire. First we remove it, and then we call retire and pass it on to the library to take care of it for us. So that's basically the interface for object base. It's quite simple, and only basically retire is the main interface. The hazard pointer class has a lot more detail. Not only the highlighted part are actually the common case, but this is kind of what we had that we thought we needed like early this year in 2018. So there's an empty state, and actually that's not the common case, but the default constructor constructs an empty hazard pointer. That's kind of like a hazard pointer that you can move into. If you want to construct a usable hazard pointer, there's a free function for that for a construction. That's the one you can use to protect objects. Otherwise, this class is movable but not copyable, and the main functions are try protect, and basically you're giving it a pointer and a source. And it returns a bool whether it was successful or not in protecting the pointer. And it succeeds if source is still pointing to the pointer. There's no ABA problem here, so even if the pointer was put again in source, that's okay. Protect is simpler interface, is basically it will return a pointer value, and if that pointer value is not null, then it is protected. If we have other means of guaranteeing that an object is not removed, let's say we have a lock, we can just say reset protection, and we don't even need to check a source or anything. The library will listen to us that, okay, we as users guaranteeing that the object is not removed or not retired yet, and it will start a protection epoch for that hazard pointer and end what it was protecting before that. If you want to end, if you want to end protection, we can call it with the null null argument. Then it will just like stop protecting whatever it was protecting. The other functions are like empty, and then you can swap to hazard pointers where they will continue protecting whatever they are protecting. It's just they will swap identity. And if one of them is empty, one is not empty, they'll swap that. Let's look at the usage example of that interface. So again, we're going back to the example I showed in the beginning with pseudocode, but in this case, we're implementing it using this API. So the protected object, as I mentioned, it's derived from the object base, and it's giving the type as a template argument. We have this is the constructor for an active hazard pointer. We use that hazard pointer to get a protected pointer value from the source. Once we get that, we know that that pointer is protected, and we can use it. I don't show it here, but similar to RCU reader, this is an RAII interface where at the end of the scope, the hazard pointer will end protection, and it will be destructed. From the remover side, they remove the object, and then they call retire. So that's kind of a complete usable case using this API. Okay, so that's it. I mean, that's the TS2 API. I wanted to spend more time on the coming part, where basically we are looking at what questions we want to ask for the TS2 process, the technical specification process, to learn from. And also, as we go, like even in the last, let's say, 6 or so months, we learned a lot in that period, but we're not chasing that interface in the TS proposal. So one of the biggest things, like topics that actually we studied and added is link counting and integrating it with hazard pointers. So here are some motivating examples. There are kind of limitations of that interface that I showed already. We protect single objects. We might be able to use hand-over-hand traversal to protect 2 objects using 2 hazard pointers, but we don't protect a whole list. And that problem is we will end up with conditional traversal, where at some point say, oh, we cannot proceed, let's go back to the head of the list. And that works in some algorithms, but what I'm going to show now, it doesn't work for this algorithm. So in this case, a thread wants to protect object A, and it uses the source, the head pointer as source. So it succeeded, of course, I mean, as guaranteed by the API for, the specification for protect, it will return a value. So unless head is null, it will protect an object. So that's fine. We protected A. Actually, for our operations, for that thread, it needs to access B, specifically B. There's no wiggle room there. We need to access B. But then in the meantime, actually, A got removed and retired, which is fine. We're protecting it. So that's fine for A. But then also B got removed and retired. That's the problem. We're not protecting A by that hazard pointer. And now, the other threads check hazard pointers, and they find that B is unprotected. So what do? They reclaim B. And the problem now is that the thread that needs to access B cannot start over from head. The head pointer has just moved on beyond B, and B is gone. So that's obviously not a good solution. Of course, we can combine this with reference counting or atomic share pointer, that sure will work, but then there's a lot of overhead in that, unnecessary overhead. So what I'm going to talk about will be, like shortly, we'll actually integrate that in hazard pointer. Also, another thing that can be solved with atomic short pointer, but right now in the TS2 interface, not by hazard pointers, is uncertain removal. So now we have an object A that has 2 pointers to it, source 1 and source 2, and some thread removed the link from source 1. Does it call retire? It doesn't know, because it doesn't know if there is another concurrent thread that already removed the link from source 2. So in this case, it's uncertain removal, and hazard pointer doesn't have a way, because we have the retire interface, it doesn't have a way of knowing when to call retire in this case. Again, we can use reference counting. It's just adding a burden on the user or overhead if they use atomic shared pointer. So we'd like to integrate that in the interface. So now I'm going to go through an algorithm and kind of at a high level for dealing with links. So we're not doing reference counting as in readers, counting reader references to the objects. We're only counting links. So readers will not be affected by this at all. There's no overhead for readers. We're going to manage 2 link counts, one for immutable links and one for uncertain and or mutable links. And there are some exceptional cases where actually we could reason and say some mutable links will not count. So I'll mention that as we go. But basically the distinction between like immutable links and the rest. One way to integrate, I mean, the way to integrate it with hazard pointers is we're going to think of hazard pointers collectively as one link, one immutable link. So that's kind of, it will allow us to like check hazard pointers in parallel without, you know, we don't care which link we decrement when we check hazard pointers. It will count as one immutable link. So for example, here's like we have a head pointer with a certain removal. So we'll reason about that and say we'll discount that link. But then we have let's say a FIFO list, which means that the links are immutable. So in that case, like you can see that object A has, it doesn't really have any inbound immutable links, so it will have count of 1, because that count of 1 represents hazard pointers collectively. Because, you know, someone might be protecting that object, so we'll give it a count of 1. When it goes through the checking of the hazard pointer and we find out that actually the object doesn't match any of the hazard pointers, then we decrement that count of 1. Whether we actually decrement or not, that's an optimization. But logically, we as if we're decrementing that count. While object B, it has 1 inbound immutable link and hazard pointers count as another count. So that's why it has 2. The other kind of pattern is objects that have inbound mutable or uncertain links. In this case, it will have a count of 2 for the mutable links and a count of 1 for the immutable links that is representing hazard pointers. Okay. When we have an object that has inbound links that are descending from uncertain links, we actually treat these links as uncertain. So just like bear with this kind of, trust me on that, and that's kind of part of the algorithm. If we reach the point where actually decremented the uncertain links to 0, then we know that, okay, now we can retire the object. But before we retire the object, we actually say, okay, if there are any descendant immutable links, we're going to downgrade them from uncertain to being immutable. So now, so that's when we take the decision to actually retire an object. Of course, we can retire an object explicitly if we know for sure that there's no uncertainty about when it is being removed. Okay, now if we retire an object and we find that it's not protected by any hazard pointer, like we went through the hazard pointers, then we will decrement the immutable link count by 1. And finally, when we get to the immutable link count goes to 0, then we're going to reclaim the object. But before we do that, we're going to iterate over its descendants and decrement their immutable links. If it goes to 0, we reclaim the descendant. And also, if they have uncertain mutable links, if they're outgoing uncertain mutable links, then we unlink the children. And that might trigger retirements and so on. So that's kind of outline of the algorithm, and it's in open source code. I'm going to give the link at the end. So that's the API proposal. It doesn't quite match the code, but actually that would be a valid API for this, for link counting. Basically, we have a base template similar to object-based, but in this case, it handles link counting. We have a function that actually increments the counts. It takes a bool whether it's immutable or not, and it takes a bool to say, is it safe or not? Like, do we need atomicity or not? So if we don't need atomicity, we can actually save an atomic operation, atomic instruction. It has retire similar to the object-based that I showed earlier for the TS2 interface, but it also has unlink, which decrements the uncertain link count, and that might trigger retirement. So it's kind of implicit retirement as opposed to the explicit retirement. Finally, because of this there are lots of decisions being taken inside the library. So actually, we might not have a chance to pass custom deleter to the function. So actually, we have a function to set the deleter before the object is removed. So before there's any uncertainty about whether the object is removed or not. From the user-defined part, they actually have to define a function template called push links, and that will take the library will tell it, we want you to give us immutable links, or we want you to give us mutable links, and it gives us a set. That set is, we define it in the implementation, but then it's a template argument, and all what it needs, it should support something that is like push pointer. Finally, in some cases of heterogeneous links from one type to a different type, node of different type, then we actually use this hazard pointer source, which its main functionality is, it behaves like a link, but also at destruction, it unlinks the destination. So we're going to look at a couple of examples here. These are real-life examples, heavily, used code. One is an unbounded queue. It's in the open source Facebook Folly library, and basically, it's the FIFO queue is composed of a FIFO singly linked list of segments. Each segment supports some number of queue elements, so the cost of construction destruction is amortized over, let's say, hundreds of elements. We're always appending to the tail, so the links are immutable in this case. Head is mutable, but it's certain, so actually we can discount it, but we as users, or library writers in this case of the unbounded queue, we take responsibility for calling retire explicitly. So that's we'll ignore the link count for head. And head never overtakes tail, so we will not care about tail, so it doesn't matter in the count. So now you can look at here, the first one has count of 1, the rest of the queue has count of 2, because as I mentioned, hazard pointers collectively count for 1 immutable link for each object. We do the initial and final increments and decrements non-atomically, so actually that saves a lot of atomic operations. So actually all what we need in the lifetime of each segment is one atomic instruction in the common case, in case like without like just having contention at the time of decrementing the counts. And we can reclaim many segments in one check of hazard pointers. I'm going to go through an example here of like what happens to this this queue. It has like 4 elements. We're going to like remove 3 of these segments. They are removed and retired. We code retire explicitly, so you can see that the counts are still, as they were. Now we check the hazard pointers, and we know that we don't guarantee that we're going to check them in the order A, B, C. That's fine in whatever order. So in this case, we check B. Let's say B is checked first, and we find that it's not protected. So we decrement the count from 2 to 1. And because it's then now we check A. A is also unprotected, but then the count is already 1. So A is reclaimable right away. So when that happens, as I mentioned in the algorithm, we go through iteratively over its descendants and reclaim whatever is reclaimable, or decrement the counts for what has more count. So in this case, we find that B is reclaimable. We reclaim B right away. When we reclaim B, that triggers decrementing the count for C. So it went from 2 to 1. Now, and finally, we reclaim A. That's for A. Now we're checking C, and we find that C is unprotected. C is reclaimable. So we look at its descendants. We decrement the count for D. It went from 2 to 1. And finally, we can reclaim C. So we were able to reclaim basically whatever is ready, any number of segments in one check of hazard pointers. Whereas if we used something like atomic share pointer, we would have to wait for like one at a time checking of hazard pointers to reclaim the segments in that queue. Okay, that's so as I mentioned, we take 1 atomic instruction per segment, and we reclaim a large number of segments in one check. Now we'd look at a different example that's also from the Folly library. It's the concurrent hash map. And it's a hash table with chaining. Each bucket is a singly linked list. So it would look like that, and these are kind of the counts. The bucket heads are uncertain mutable links, so they count for 1. And then the hazard pointer library in general, hazard pointers in general count for 1. The links between the threads, like from B to A, between the nodes, counts also as mutable links. So that's why we have these counts, 1 and 1 for B and A, and these counts are like set non-atomically. They don't need to be atomic. Anyway, nodes may be linked from multiple bucket arrays due to resizing. So for example, let's say we resized and changed the bucket from X to Y, and now we keep links. So because we support iterators, so actually we'll keep that bucket alive if there's an iterator that's protecting it. By the way, each iterator has 3 hazard pointers. I'll mention that. So now you can see what happened here. B has count of 2. There's 2 inbound uncertain links. The removal of bucket arrays is certain, so we don't use linked, we just use the obj base, the original one that is in TS2. But links to nodes are uncertain, so we use the obj base linked. And because bucket arrays and nodes are not the same type, so actually we use the links from the bucket array to the nodes, to the head of the node, is a hazard pointer source. I mentioned for traversal, we use 3 hazard pointers, and the initial and the final counts don't need atomicity. So actually, we could end up with, in a common case, doing 0 atomic instructions for reference counting, for link counting. And read-only operations have 0 overhead for link counting. But then this is a caveat, is that nodes are retired 1 at a time because of the uncertainty of the removal. So actually, we have to keep this linked list short. We cannot have like thousands of nodes in the, so I mean, that's why it's a hash map. we actually want to have the load factor good enough that it doesn't have long lists. I'm going to go through an example which will demonstrate this kind of the lifetime of a bunch of operations. So we start here with an empty bucket head X. We insert A. Yeah. It has count 1, 1 as expected. Now we push B LIFO, and now it has 1, 1. Now we do resizing. So and A and B happen to be rehashed to the same bucket. So now we have a new bucket Y that is pointing to B and A, but then X still points to them. So that's why the count for B increased. There could be some iterator that's protecting X, so X might be still alive and traversable. Now let's continue from there. The next operation, let's say insert C. So now we have C is pointing to B instead of the bucket head, but still it goes with the counts of 1 and 1. Now we remove B, and you notice that we can't really retire B because it has an uncertain. Oops, sorry, it has an uncertain link. Then we take it from there and actually remove A. Then it becomes also A is kind of removed but not retired. Now we check the hazard pointers and find that X is not protected. So we look at the descendants, we unlink B, and now B is completely retired. And then we reclaim X. Now we check the hazard pointer again, and we find that B is reclaimable, so we reclaim it and unlink A. And now A becomes retired. And finally, we do another check and find that A is reclaimable and reclaim A. Okay, so this kind of like describes the link counting algorithm and are real like complicated use cases that depend on it. So that's a good extension of the TS2 API. I'm not going to go through this, but this is kind of a list of questions. A lot of them are in common with RCU that Paul went through, and some are not. But it's kind of these are questions that actually we want to learn in the TS process. Finally, these are references. The paper numbers are 566 and 1121. And the Foley library is on GitHub, and there's the general hazard pointer implementation, and also the link, the one that supports link counting, and the examples of the unbounded queue and concurrent hash map. There's also a test case that is kind of contrived, but it's actually very interesting that it has uncertain links to that is predecessor of immutable links, and actually we are able to retire a whole structure in one pass, and also we can reclaim a whole structure in one path, even though it's uncertain removal. And thank you. I don't know if we have time for a question or two. And Paul, please, if anybody has a question for me or Paul, thanks.